So suppose you have a cylinder, and this end of the cylinder is closed. So I'll just draw it like this. And on the left end of the cylinder, you've got this piston arrangement. So it's airtight or watertight, and you can just push this piston in. Okay, so that's the arrangement. So it's kind of like a syringe, but the right side is completely closed off. Okay, so suppose this is, and just for, just to have some concrete numbers, let's say that the length of the piston is 100 centimeters, which is 1 meter. And let's say that its diameter is, its radius is 10 centimeters. Okay. And okay, and let's say it's filled with air. All right, so that's what we have. Now, suppose you want to push this piston in and squeeze the air, right? Can you do it? The answer is you can. You can certainly push it in. You won't be able to push it in all the way. It'll get harder and harder to push in, but you can certainly squeeze the air to some extent. You can just do it with your fingers. All right, so squeezing air is no problem at all, right? But suppose instead of air, you have water over here. Now, will you be able to squeeze it, squeeze the piston? What do you think?
Can you, because it's still a fluid?
Okay, so Alex thinks we can. Anybody else have any opinions? Do you think you'll be able to squeeze the piston?
I think yes, but not as much.
Okay, that's another good opinion. Anybody else have any thoughts on that? Okay, the correct answer is no. You will not be able to squeeze the piston at all. You can bring in your bulkiest and strongest football playing friend and have them take a go at it. They'll not be able to squeeze the piston at all. And that is because of a property of liquids. So liquids are often said to be incompressible. And I'll just qualify what this means in a second, but it means that you simply cannot squeeze them at all. Let's just see why this is the case. The reason that this is true is because of something that we learned yesterday at the end of the last chapter when we were talking about the bulk modulus. So remember that the bulk modulus was defined as the change in pressure divided by the fractional change in volume. And there was a minus sign here. It's not that important. That was the definition of the bulk modulus, right? Now, the bulk modulus, so the bulk modulus is a number which tells you how difficult it is to squeeze that material from all directions by applying pressure from all sides, right? And that's essentially what you're trying to do here. You're trying to squeeze the volume of water inside our cylinder. Now, the bulk modulus for water is extremely, extremely high. Actually, it's high across the board for all liquids. And so water is no exception. But the bulk modulus for water is 2.15. We'll just take it as 2 times 10 to the power of 9 pascals. You can see that the unit of bulk modulus will be pascals because pressure is force divided by area, and that's pascals. And delta V over V will not have any units because it's a ratio. So the unit of bulk modulus is also pascals. And the bulk modulus of water is this stupendously high number of 2 times 10 to the power of 9 pascals. So let's say that your goal is to just squeeze the piston in by 1 centimeter. That's all. Just want to squeeze this piston in just by 1 centimeter. Let's just calculate how much pressure that would take, right? Given the bulk modulus of water. So if the piston is if the cylinder has a total length of 1 meter and you're reducing its length by 1 centimeter, that means delta V over V would be 1%, right? So delta V over V in our example is just 1% or 0.01. So the pressure, the difference in pressure that you would have to apply, delta P, which is basically the pressure in excess of the pressure that already existed, which was atmospheric pressure. So it is going to be 2 times 10 to the power of 9 pascals multiplied by the delta V over V, which was 0.01. If we want to squeeze it by 1 centimeter. That makes sense? So now let's calculate how much force do we need to apply in order to get that pressure, right? So what is the relationship between pressure and force?
Pressure is equal to force applied over a certain area.
Yeah, force divided by area. So force would simply be the pressure multiplied by the area. So the pressure we just calculated, the excess pressure we'd have to apply is this. So if you times that by the area of the cylinder, the cross-sectional area of the cylinder, you get the force that you need to apply, right? So let's do that. 2 times 10 to the power of 9 pascals times 0.01 times the area of the, so we assume that our cylinder has a 10 centimeter radius, right? So that's 0.1 meters. And so the area would be pi times 0.1 squared. That makes sense? So what is this going to be? So this is 10 to the power of minus 2, another 10 to the power of minus 2, and then you have 10 to the power of 9. So that would be 10 to the power of 5. Oh, and pi is approximately 3. So yeah, approximately 6 times 10 to the power of 5 pascals, ballpark. Sorry, and this is area. So this is meter square. So Pascal is newtons divided by meter square. So the meter square will cancel out. And so you have, I'll just write it as newtons divided by meter square so it's clear. That's what a Pascal is. And so you're going to have 6 times 10 to the power of 5 newtons is the force that you would have to apply in order to move the piston by just 1 centimeter. That makes sense? 6 times 10 to the power of 5 newtons. How much force is that? If you know that, you can easily think of force as weight, right? And you know that weight is mass times gravity, mass times g. G is approximately 10. So this is approximately the weight of 6,000 kilograms. That would be around 6 times 10 to the power of 5 newtons, right? 60,000 kilograms. Oh my goodness. 60,000 kilograms. When I just did work through this before, just a few minutes before class today, I made a mistake and I thought it's 6,000 kilograms, and I was just looking up what is 6,000 kilograms, and that would be the weight of a large African elephant would be 6,000 kilograms, but 60,000 kilograms, is that right? That's right. So that the force that you need to apply to squeeze this piston by 1 centimeters is 60,000 kilograms, the weight of 60,000 kilograms. That would be the weight of like 2 fully loaded Mack trucks or something like that. That makes sense? So that is the amount of force that you need to apply to squeeze this piston, if it's filled with water, to squeeze it by a tiny amount of 1 centimeter. That makes sense? And that is what is meant by the fact that fluids are incompressible.